Hello, good afternoon. I hope I am audible. So,
Yes, sir.
for
Good
those
afternoon, Mr.
who could
Audible.
not, yeah, okay. So for those who could not join during the last session, what we had during last week, apologies because I couldn't configure that Zoom meeting properly. So those who were trying to join last week were not able to join through the meeting. But despite that, we have uploaded the discussions. Actually, what I intended to go through the sessions, I've uploaded that in YouTube, so you can go through that at your own leisure. So this, I hope you have been going through the lectures. So for this week, the topics would be a basic introduction to kinematics or kinematic modeling of robotic manipulators. So, yeah, just introducing myself, I'm Isaac John. I am a PhD scholar from IIT Palakkad. So, I'll be handling the weekly live tutorial sessions on the topic mechanics and control of robotic manipulators. So, this is the session two regarding all the topics that we have discussed in week two worth of lectures. So, yeah, we'll move on to the topic. So, for this week, we have basically covered the topics on kinematic parameters. Then we have also given a brief introduction to DH parameters and how to assign DH parameters to typical robotic manipulators. So it's essentially a well-known procedure or a well-known algorithm where you can represent the motion of rigid bodies, interconnected rigid bodies, using something called DH parameters. And we have also explained with a few of examples how to assign DH parameters to a robot and using the DH parameters, how to derive the kinematics of a robot manipulator. So, the purposes of this session is to once again, the purposes of this session is to briefly recall what we discussed, just to briefly summarize all the topics regarding week two, and then we will for the later half of the session, we will also solve some sample tutorial questions, which is similar to what you can expect for the week two quizzes. Okay. So regarding the summary, we'll start with the summary of the topics, the week two worth of topics. So, as I've already told you in the beginning, we basically use frames uh, to pass the information between two links. Like for example, if you have two links like this is one link, and this is another link. For example, of any robotic manipulator, and you have joints. Maybe if you call this as z-axis, z1 axis, and maybe this could be z2 axis. And these individual links I'll label this as link 1 and link 2. And these links are able to rotate about their own respective axes. So if link 1 is free to rotate about z1 axis and link 2 is free to rotate about z2 axis. And the reason why we require frames is that since we are only dealing with rigid bodies, in kinematics or in deriving the kinematics of a rigid body robot, we can essentially replace this rigid body with maybe a coordinate frame of reference. For example, if I attach a coordinate frame of reference on rigid body 1, I label this as Z1, X1, and Y1. Or if you follow the right-hand screw rule, X1, Y1, Z1, and I firmly attach another frame of reference on link to something like X2, Y2, Z2, then all the relations may be relative positions between these two rigid bodies, relative orientations between the two rigid bodies, or if you want to define attributes of a particular rigid body, such as the center of gravity or moment of inertia, you can basically use the frame of reference which are attached onto the rigid body. For example, a relative position and orientation between these two rigid bodies can be passed over or can be represented using the frames of references Like for example, if there is a finite distance between these two frame of reference, that could be the distance between the rigid bodies, because the relative position between any 2 points of a rigid body will never change. And similarly, with the case of orientations as well, the angle between the corresponding axes of individual frame of references can also be used to communicate the orientation differences between the two rigid bodies. And further, in case of a robotic manipulator, you may also be aware that they cannot have all 6 degrees of freedom because they are connected by joints. Consider one instance where a rigid body is not constrained at all; it's free to move in space. So, if that is the case, then a rigid body can have all 6 degrees of freedom, which is 3 translation and 3 rotations. But if rigid bodies are interconnected using joints, such as a revolute joint or such as a prismatic joint, they will lose a few of the degree of freedom. For example, a revolute joint can only have a single degrees of freedom while having 5 other constraints. So all these relations, actually, the kinematic relations, the positions, the orientations, how the constraints can be propagated from the base, from forward to all the way from the base to the end effector, or how the forces can be transmitted along the robot manipulator. All these things can be facilitated using the frame of references that is attached onto the robot manipulator. So this is exactly why we require a convention, actually, because there are different kinds of robotic manipulators. For example, something as simple as a 2R robot. The reason I call this a 2R robot is it consists of 2 revolute joints, and hence the name RR manipulator. Or you can call this as a 2R manipulator. This is R1, this is R2. And here you can have an end effector or a gripper or any of those sorts. And here, this side would be fixed to the ground, and this side is where we attach the tool. Right. So this is one of the most studied or one of the most elementary robot manipulators that one can have. And similarly, there are 6 degrees of freedom robotic manipulators, which has all rotational as well as translational capabilities. So, given the variety of robotic manipulators that we have, we actually need a basis or a convention so that we can we can have a uniform, methodology to assign frame of references to any such robotic manipulators. And speaking of frames, if you again consider a 2R robotic manipulator or any n degrees of freedom robotic manipulator, uh, once you have assigned frames, there will be, if the number of degrees of freedom of the manipulator is n, there will be n plus 2 frames that you are required to attach, right? For example, if you again consider a 2R manipulator like so, with 2 revolute joints, so this a 2R robot will have 2 rigid bodies connected by two revolute joints. So the first link would be connected to the base using this R1 revolute joint, and the second link and the first link are connected using a second revolute joint R2. So here the degrees of freedom basically means the number of controllable inputs that you need to give as input to a robot manipulator. So in this case, for this RR robot, the degrees of freedom or DF for in this example would be 2, because you have to give 2 controllable inputs to control this robotic manipulator. And how many number of frames do we have? So obviously we have 2 links, so at least we will have a 2 frame of references. So one would be here, maybe Z0, X0, and Y0. And this would be Z1, X1, and Y1. So two frames of references attached to that to their respective rigid bodies, and there would be two more frame of references. Sorry, instead of 0, this would be denoted as 1, so that the number of the link number as well as the number of the frame of reference can be matched. Right? Frame 1 for link 1 and frame 2 for link 2. And this the two more additional frames, the +2 factor here accounts for one more additional frame that would be here at the end effector or at the tool, which could be labeled as Z3, X3, and Y3, and one more frame of references that would be at the base or attached to the ground. That would be Z0, X0, and Y0. So in total, for an NDE of freedom, you will have n+2 frames, or for in this particular examples, for a 2D of RR manipulator, you will have 4 frames, 2 attached on each of these links, and one to the ground and one to the end effector. So and if you have n+2 degree of frame of references, so how many parameters would you require to establish the relationship between all these frame of references? Because typically a frame of reference can have 6 degrees of freedom, right? If you consider this to be fixed to the ground, if you consider the 0th frame to be fixed to the ground, the first frame can have 6 degrees of freedom, right? It can move, it can translate along 3 directions. It can also rotate along 3 independent directions. So considering all the frames, you would require 6 times n+2 parameters for a robot as per classical mechanics. Right, each of these frames will have 6 degrees of freedom. So n+2 frames will have 6 times n+2 parameters. So to counter this or to somewhat minimize this large number of parameters to the need to have, in order to minimize that, we have a convention, fortunately, in robotics, which is introduced by two scientists called Jacques Denavit and Richard Hartenberg. They have basically introduced a convention in order to standardize the coordinate frames of spatial linkages. So this convention is basically named after these two scientists, Denavit and Hartenberg. We call them as Denavit and Hartenberg parameters, or DH parameters in short. So instead of 6 parameters, we only require 4 parameters. 4 parameters associated with particular convention for attaching the reference frames. Excuse me 1 second. Yeah. So instead of 6 frames of reference, we would only require 4 frames of references. And how do we attach these frame of references? That also is as per some convention, actually, which we will get on to later. Yeah. So out of these 4 parameters, we have 2 of them are called link parameters, and the remaining 2 are called join parameters. So the link parameters basically represents the information between 2 consecutive joins, and the join parameters represents the information between 2 consecutive links. So it could be easily misunderstood because join information is transferred using link parameters, and link informations are transmitted using join parameters. So we will look into this in with more details in the upcoming slides. So yeah. So what basically does this DH parameters do? So DH parameters, or the link parameters, specify the relative position and orientation of 2 successive joins. So there are 2 link parameters to do that. So the one of them would be a link twist angle, and the second is actually the link length angle. So like, for example, if you have 2 links like this, so I'll represent this to be one link. We have an axis like so. I'll call this as zi minus 1. And we have another axis that is out of plane, and which is also orthogonal, or which is at 90 degrees with respect to zi minus 1 axis. So I'll label this as zi axis. This is zi minus 1, zi, right? And the link parameters essentially relates the position and orientation between two successive joints. So if you consider these joints to be, adjacent to each other, so one of the joints is facing upward along the vertical direction, and the other is essentially facing out of plane, like so, perpendicular to each other. Now you would require two parameters to uh, specify the position between these two axes, the distance along the normal distance between these two axes, and also you also need one more parameter to specify the relative orientation between these two axes, right? Which is basically 90 degrees. So if you rotate this axis 90 degrees, you will get the orientation of zi axis. So you need two parameters to for that. And the first parameter is called the link twist angle. It is basically, as per the definition, this is nothing but the angle between zi minus 1, angle between zi minus 1 and zi along xi minus 1, right? So what is this xi minus 1? So again, as per the DS convention, you can refer the reference textbook. The way to select the direction of xi minus 1 would be, so if you have zi and zi minus 1, xi minus 1 would be orthogonal to zi and zi plus 1, right? So zi is along this direction, zi minus 1 is along this direction. So zi will be along this direction, which is orthogonal to the adjacent axes. So I'll label that. I'll label like this. So this would be xi minus 1, right? So the link twist angle would be the angle between zi minus 1 and zi along xi minus 1. So if you rotate 90 degrees about xi minus 1, zi minus 1 will be aligned with zi, right? So that is what we call the link twist angle over here, right? Which takes care of the relative orientation. And the second link parameter would be link length. So link length is basically the perpendicular distance between zi minus 1 and zi along xi minus 1. So the orientation is along xi minus 1. The position is also along xi minus 1. So once you have rotated, once you have established identical orientation between zi minus 1 and zi, you would need to map the distance between these two frames of references along xi minus 1. So that would be parameterized by the parameter called link length. And the reason is because link length is basically nothing but the length of this link that we are dealing with. A link or a binary link which has two joints, its defining characteristic is its link length actually, which is nothing but the distance between these two joints. So if you traverse along xi minus 1 by ai minus 1 units, which is nothing but the link length, you will be also able to map the distance between these two frames. So that is what link parameters are about, which specifies the relative position and orientation between the two successive joints, right? So that is link parameters. Then what about joint parameters? We have so far covered two parameters out of the four DS parameters. The remaining two DS parameters are joint parameters, which specifies the relative position and orientation of two successive links. Earlier, we were talking about joints. Now we would talk about links, relative position and orientation of links. So we have one such joint parameter called joint angle, which is nothing but the angle between xi minus 1 and xi along zi. And joint distance is basically the perpendicular distance from xi minus 1 to xi along zi. So I'll give you two examples for that. Again, considering the RR manipulator having two rigid bodies connected using two revolute joints. So you always fix the z-axis first, which is the obvious choice because z-axis always aligns along the joint. So in this case, the revolute joints are out of plane. So z-axis are also out of plane. So z1 is like this. Z2 is also out of plane. And x-axis would be, x1 would be perpendicular or orthogonal to z1 and z2. In this case, they are parallel. It can be chosen along any direction. But for convenience, we will choose it along the link length z1. And z2 would be along the link length of the second link, x2. This is link 2. This is link 1. And the relative orientation between x1 and x2, you can call this as theta 2, as this is. Okay, so we may have some technical issue. So within 10 minutes, this meeting may terminate automatically. So I will have to ask you to rejoin the meeting because the Zoom, as of now, the current Zoom will only allow you to have the session continuously for, I think, around half an hour. So once the meeting automatically terminates, you can again rejoin the meeting. I'll make sure that this won't happen from the next week onwards because we still haven't acquired the license. So if the meeting terminates, you are free to rejoin the meeting. Okay, so continuing with respect to the joint angle. Joint angle is basically the angle between xi minus 1 and xi along zi. Right? So I'll consider z1 as my xi minus 1 and the frame 2 to be my the ith frame. This will be the I minus 1th frame. This will be the ith frame. Right? So the angle between xi minus 1 and xi, right? Xi minus 1 would be along this direction. Xi would be along this direction. And their relative angle is given by this variable theta 2. And it is actually measured along z2. Because theta 2 is actually is basically a variable associated with frame 2. The relative orientation between xi minus 1 and xi is measured with respect to zi. In this case, it does not matter because z1 and z2 are more or less parallel to each other. So if you measure it with respect to z1 or z2, it does not make much difference. But we always associate the joint parameters with respect to its corresponding link as well as its corresponding frame. So in this case, the angle between xi minus 1 and xi along zi is theta I. That is what we have as the joint angle. And one more distance that we haven't taken care of is something called the joint distance. So I'll have to resort to a different view. For example, consider maybe a front view of two links like this. So this will be I minus 1th link. This will be the ith link. And ith link and I minus 1th link are connected using the ith joint. And the axis along the joint will be labeled as zi. So if there is a finite distance or if there is a finite distance between these two links, maybe I'll call this offset as di, which is measured along zi. right? This distance, to accommodate this distance, we will basically take care. We will basically take care of this offset using something called the joint distance. The fourth parameter called joint distance. So it's basically the perpendicular distance from xi minus 1 to xi along zi. So we will basically implement all these ds parameters in a few of the following examples that we will come across, which will hopefully make it more clear. Right? Yeah, and this is one of the examples where one can use the ds parameters, because this is basically you can consider this to be a part of a robotic manipulator. So this would be link I, this would be this would be link I minus 1, this would be link I. So the essential thing to be noticed is that you have a link like this, which will have two joints at one end here and another end here. And what do we call these sort of links having two joints? Because a link like this can only connect to two other links like this, right? And we call the name of these sort of links, we call them as binary links. Binary links. And there are other sort of links. We actually have ternary links, which have three joints like this, which can connect to, three other links. But from the context of a serial robotic manipulator, we assume that the robotic manipulator is assembled, or it's actually is made up of binary links. For example, by serially assembling binary links with the help of a single degree of freedom joints. This is a very generalized expression. So these could be binary joints such as revolute joints, or single degree of freedom joints, revolute joints, or prismatic joints, right? Because as you may know, there are joints that has more than 1 degree of freedom, such as a ball and socket joint. We call them as spherical joint. So we have a ball like this, which is free to rotate about a socket, similar to how our shoulder joint moves. So ball and socket joints will have 3 degrees of freedom. And there are other joints such as a universal joint, which has 2 degrees of freedom that can rotate about two perpendicular axes. So the thing is, while kinematically modeling a serial robotic manipulator, we assume that the entire robotic manipulator is made up of binary links, and each of these binary links are interconnected using single degree of freedom robots. And if the robot has something like this, a spherical joint, we can decompose a spherical joint as three intersecting revolute joints. Three intersecting and mutually orthogonal revolute joints connected by, massless and zero length links. So whatever be the case, you can always approximate any robotic manipulator uh, uh, as a serial connection of binary links connected with single degree of freedom joints. So if that is the case, what we require is you need to map the motion of the tool tip here at the tip to a coordinate frame that is rigidly fixed to the ground. For example, x0, y0, z0. So you need to have some sort of a mapping. Like, in order for you to really control a robot, you would require to know the position and orientation of the tool with respect to a fixed frame of reference that is attached to the base. So the way to do this is to successively transmit or transfer all the positions and orientations of all the links successively from the base to successively from the tooltip or the end effector all the way to the base. And you can do so by attaching frames of references on each of these links, right? So once you have attached a frame of reference on a rigid body, the frame is actually a representative of the rigid body. So now it has now turned into a matter of transmitting information between this frame of references to exactly know what each of these rigid bodies are doing. So the first thing in DH convention or DH representation is to attach or is to fix individual frame of references onto their corresponding onto the corresponding links. That is the first thing that we require. And despite this, there are two well-known implemented representations of DH parameters. So the one that we use for this course is called non-standard DH representation, right? And I hope you can recall this from the lectures of Professor Shantakumar. So the main difference between a standard and a non-standard DH representation is where you attach the frame of reference on a rigid body, right? For example, if you consider this to be a rigid body or a binary link, you can actually label the two ends. This is one end of the binary link, and this is another end of the binary link. You can name or so a binary link has its two ends, which can be labeled as proximal end, and the other end of the binary link can be labeled as distal ends. And we name the end proximal, which is nearer to the base or nearer to the ground or ground. And we label the end distal, which is facing towards the end effector or the tooltip. Okay, and the main difference between the standard and non-standard DH representation is in standard DH representation, we attach the frame of reference on the distal end. Attaches frames of reference at the distal ends actually. And in non-standard DH, attaches frame at the proximal edge. Right. So in this case, since we are following the non-standard representation, we attach the frame of reference. So like if this is the ith link of a robotic manipulator, we attach the frame at the proximal ends. So one example would be, this would be Zi, this would be Xi, this would be Yi. And there are a lot of advantages if we are following using the non-standard DH representation, because if you consider this particular link, the center of gravity would be somewhere in the middle, something like this, right? Let this be the COG. And if this is the frame of reference that is attached at the proximal end, if you want to go to the COG, it will be more or less along the positive XI axis. You can see it's along the positive axis. But if you are attaching a frame of reference at the distal end, maybe, for example, if you are attaching a frame of reference like this, Xi, Yi, and Zi, to label the attributes such as COG, you will have to come along the negative direction, along Xi. So like this is the drawback of using the standard representation. Like if Xi is along the positive, is along the forward, COGs and other attributes will always be represented as negatives. But in case of non-standard, COGs and all those things will turn out to be positive, because COG is something that is fixed, is a fixed attribute to the link. And yeah, the frame is also fixed to the link. So like this, the mapping between the frame of reference I and COG is always going to be constant, and that too positive. That is one such advantage of using the non-standard DH representation, right? Okay, so now that we have established a difference between non-standard and standard DH representation, and why we are using something like that, we will also go on with how to assign the frames of references to a robotic manipulator. So the first and foremost thing uh, to assign a frame of reference is to locate the kind of joint and the direction of the joint. So if you consider this example, so maybe this it's obvious that the axes point along this direction. The first axis, or the minus 1th axis, point along this direction, and the ith axis points along this direction. So the first thing is to fix the axes. So we have already fixed the axes as zi minus 1 and zi, right? So you can do this for all the joints of a given robotic manipulator. Okay, yeah. For the second thing, like as I have explained, is to fix the direction of the x-axis. X-axis for I minus 1th frame. So the procedure to fix or to locate xi minus 1 is to first compare the directions of xi and xi minus 1. And xi minus 1 would be along the common normal between zi minus 1 and zi. So like for in this example, if I extend this something like this, so zi would be lying along the common normal. So if I draw this to be the common normal, I hope you can see the common normal is normal to zi minus 1, and it is also normal to zi. So this one, xi minus 1 would be, yeah, xi minus 1 would be along the common normal. And same thing for xi. Like if you want to fix xi, you have to first consider the direction of zi. And somewhere over here, you will have zi plus 1. So comparing these two frames of references, you can actually fix the direction of xi. Right? So now that we have established zi minus 1 and xi minus 1, we also have zi and xi. You can also, using the right-handed thumb rule, you can also always locate the y-axis also. Maybe yi minus 1 would be along this direction, and yi would be along this direction. But you should also note that the y-axis is not included in the DH representation. All that matters is the z-axis and the x-axis. And it is also important to note that this is what you see over here is the I minus 1th link, and the frame I minus 1 is rigidly attached to I minus 1th link. And here in the case of link I, the ith frame is rigidly attached to link I. So to propagate the information between I minus 1th frame and ith frame, what you require is you have to first translate. You can only translate and rotate. You can only manipulate these axes along x-axis and z-axis. There are no transformations along y-axis. So what you have to essentially do is that you have to map this axis through successive rotations and translations onto this axis. So we'll start from base and propagate in a similar fashion until we reach the final end effector. So the order of the transformation is given as follows, right? We first have that link parameters. The first two would be associated with link parameters, and the remaining two would be associated with the join parameters, right? So our objective is to coincide or to transform I minus 1th axis to the ith axis. So the first transformation would be rotation about xi minus 1 axis, so that zi minus 1 and zi can be aligned, right? So like, as you can see, there is a finite difference or a finite angle between zi minus 1 and zi, right? So this line is actually parallel to zi. So you have to rotate along zi, sorry, xi minus 1 until zi minus 1 and zi are parallel. So you first rotate, the first transformation is rotate along xi minus 1 by an angle alpha I minus 1 until zi minus 1 and zi are parallel. So if you rotate like this, you would end up with the first transformation. You would end up with like this. So I'll label this as zi minus 1 dash, right? And xi minus 1 would still be the same because you're rotating about that axis. So xi minus 1 and xi minus 1 dash would be the same, right? Okay, so we have completed the first step. The second step would be to translate along xi minus 1. Translate along xi minus 1 by the link length ai minus 1. So if you consider the length of this link to be ai minus 1, if you translate along xi minus 1, this frame, this newly defined frame, I minus 1 dash, will reach over here, actually, right? So the second translation would be, a second transformation would be translate along xi minus 1 by ai minus 1 units. Yeah, until zi minus 1 dash and zi align, right? So once what will you get once you do that? So I'll draw it here. So this after that second transformation, this would be xi minus 1 double dash, and this will be zi minus 1 double dash. So now, as you can see, zi and zi minus 1 are aligned, right, after the second transformation. Now, the third transformation would be again rotation about zi. So this would be rotation about zi. So earlier, both of the transformation were along xi minus 1. See, both of them were along xi minus 1. Now from third onwards, it will be along zi. So basically, it does not make it much difference because now after the second transformation, zi minus 1 and zi are already aligned. But for the sake of convention, we will use zi. So we'll rotate about zi by an angle theta I. Notice that earlier we were using the suffix I minus 1. The angle were I minus 1 and ai minus 1 because the corresponding frame of references also had the suffix I minus 1. And now that we are using the frames I, the parameters will also have the suffix I, right? So third would be rotation about zi by an angle theta I until xi minus 1 and xi are parallel, right? So as you can see, there is also an angle between xi and xi minus 1, right? So I'm drawing this parallel to xi. This is parallel to xi. And now if you rotate about zi, if you rotate about zi by an angle theta, what will you get? You will get the new xi like this. New xi would be something like this. So this would be your new xi minus 1. Now this will be triple dash. And zi minus 1 double dash and zi minus 1 triple dash would be the same because the rotation is about that corresponding axis. Since the rotation is about zi axis and zi and zi minus 1 are already aligned, any relative rotation about zi axis will not change the relative orientation of zi minus 1. So now zi minus 1 and xi minus 1 are like this. Zi minus 1 is aligned along zi. Xi minus 1 is also aligned parallel to xi. Now there is one more final translation. You need one more transformation. You need to translate by this much amount. So this is basically an offset between these two frames. So if I call this offset as something like D, I'll label this as D. So the final transformation would be the translation along Zi by a units Di, so that these two frames will now be fully coinciding. Right now, both of them would be fully coinciding. So the final would be translation along Zi by Di units until the frame I minus 1 and I coincide. So this is basically how you assign frames on individual links, and then how you transform or you transmit information from one frame to the succeeding frame. So the order by which you do this transformation also matters, because these are basically linear transformations or matrix transformations. And as you already can recall, they are not at all commutative. So the order at which you do this transformation is of very high importance. So which can be represented as xi minus 1, rotation about xi minus 1, followed by translation along xi minus 1, which is then followed by rotation about zi, followed by the translation along zi. So if you multiply each of these 4x4 individual transformation matrix, you will get the final transformation matrix like this, which is nothing but the transformation or the homogeneous transformation matrix from I minus 1th frame to the ith frame. So as I've already mentioned, a robot will have n frames starting from 0 all the way to n plus 2. So you can basically assemble this transformation matrix from 0 all the way to 2, like 0T1 between 0th link and first link, 1T2 between links 1 and 2, all the way from n plus 1 T and plus T2. So to finally get the kinematic relationship between 0th frame and n plus 2th frame, you only need to multiply their corresponding individual transformation matrices 2, 3, 3 all the way to n plus 1 T n plus 2. This will give you the final kinematic relationship between the tool with respect to a fixed frame at the base. Yeah, so that is about it. And just to append to whatever I have actually mentioned earlier, just to be clear, to distinguish between the standard and non-standard formulations, So apart from what I have mentioned, there are also a couple of points. So in non-standard DH representation, which is what we are following in this course, the rotation theta I is around Israeli axis, and the joint number is same as the coordinate number. Like for example, in a non-standard case, if you treat this as joint I associated with link I, the frame number is also going to be I. But that is not the case for the standard representation. It will be always one less than the joint number. The frame number would be, or the coordinate number would be always one less than the joint number. You only need to know just the difference. You don't need to study about standard representation because we are not following that in the course. But it's always good to know the important differences between standard and non-standard representation. So this will also make the actuation forces, which is exerted on joint I, also the same place as the coordinate frame. So this would be beneficial if you once you derive the dynamic models. We will speak more on that once we derive the dynamic models of uh, robot manipulator, which is when the forces comes into play. Another thing is addressing the links geometric characters such as center of gravity are more natural in the system. Like just like what we have seen earlier, center of gravities are all center of gravities link lengths. All these attributes associated with the link, these are always much easier to represent in non-standard DH representation. But there is also another issue. In non-standard representation, there is always going to be a mix of indices such as I minus 1 and I, like so. For example, if you go back, if you look at this transformation matrix of the standard representation, all the indices are uniform. It only has the units I for a standard representation. But in case of a non-standard, whatever we are following in this course, there is actually a mix of indices I minus 1 and I, throughout the homogeneous matrix. So that is the only drawback, if you really want to call that as a drawback, between standard and non-standard DH representations. But once you get used to this mix of indices, the advantages of non-standards more or less outweighs the advantage of uh, standard formulations. So yeah, we will basically give us a brief example of how to assign the frames of reference on uh, a few of the manipulators. So the one example is RR manipulator, or the 2R manipulator, which is very widely studied. So like I've been mentioning, we have two links connected by two revolute joints. So I label this link as link 1. I'll label this as link 2. So we also have a ground. Maybe the first revolute joint, R1, is fixed to the ground, and the second revolute joint connects link 2 and link 1. So the first and foremost thing to do is to identify the axis of the joints. So since these are revolute joints and this entire mechanism is a planar mechanism, because it can only move along a plane, the revolute joints are basically out of plane. It will come out of the plane. So I'll label this to be the axis of rotation, Z1, and I'll label this to be Z2. And notice that Z1 and Z2 are essentially parallel, right? And we have now two frames. Now we also need two more frames, because for an NDOF mechanism, we have n plus 2 frames. And for in case of the base and the platform frames, you are free to choose the coordinate axis in whichever direction you please. It does not matter. Maybe since so mostly for convenience, Since Z1 is along this axis, I would rather go with Z0 to be along the same axis as well, because it's easy. You can even have it along any other direction you want, but for convenience, I will choose Z0 as same as Z1. And Z0 is always fixed to the ground, so it won't have any rotation or translations. And X1 axis, in order to fix the X axis, we'll first have to look at X1. So as per the convention, X1 would be perpendicular to, it'll be along the common normal between, it'll be along the common normal between Z2 and Z1, right? And the common normal between Z2 and Z1 would be along this line, along that link length actually. So I label this as X1, right? And X2, I'll label along the second link. I'll label this as label this as X2, and X3 I can choose it however manner I want. So I'll for convenience I'll choose it to be identical to the frame 2. So this will be Z3, this will be X3, just for the convenience. X3, this will be Z3. By convenience, I mean the transformation between Z2, frame 2 and frame 3 would be identity rotation, because they are more or less, they are aligned more or less. Yeah. So now that we have assigned the frames, what about the DH parameters? What were the 4 DH parameters? They were alpha I minus 1, AI minus 1, theta I, and DI. And this I varies from I as 1, I as 2. Maybe we can go from 3 as well. So the first 2 parameters are always associated with xi minus 1, xi minus 1. This is also xi minus 1. And the remaining 2 are associated with zi. So here in this example, we'll first start with the base frame, the frame 0. So if this is 0th axis, and I can also consider x0 to be something like this, along like this, right? So the 0th axis, since it is being fixed to the ground, is always going to be fixed. Their relative rotation and relative orientation is always going to be same. It's always going to be fixed. So now what is the transformation between the 0th frame and ith frame? Sorry, 0th frame and the first frame, right? So like for convenience, I'll also label this angle to be theta 1, and this angle, the relative angle between link 2 and link 1, to be theta 2, right? Okay, so now if you move the transformation from Z0 to Z1, what is the first transformation that we are doing? We are doing the rotation about xi minus 1 axis, so that Z0 and Z1 can be aligned, right? But since they are already aligned, like by convenience, we chose Z0 and Z1 to be already aligned. So since they are already aligned, we don't need any further rotation about x0, right? We don't need to rotate any amount by x0 to make Z1 and Z0 align. So this alpha I would be 0. And what is the next transformation? The second transformation would be translation along xi minus 1 axis, or translation along x0 axis, right? So that Z0 and Z1 would align. Earlier it was to make them parallel, now to make them align. So like since there is no relative distance between Z0 and the zeroth frame and first frame, we don't need to translate along X0. So that also makes it 0. And now what about the rotation about Zi? So the rotation about Zi or Z1 in this instance is to align X0 and X1, right? So like this theta 1 basically changes with respect to your inputs, with respect to your motor input. So as you can see, X1 and X0 are aligned at an angle theta 1, and you need to rotate by an angle theta 1 so that X0 and X1 can be aligned. So the joint angle would be theta 1. And since there is no need to translate along Z1 because they are already now coincident, you don't need any further translation along Z1. The final translation is 0. Di is actually 0. Okay, so again, we may have one more interruption in 10 minutes. So please feel free to join if the meeting gets terminated after 10 minutes, because we'll be solving a few sample exercises in the upcoming slides. Okay. Okay, now we have basically identified the transformation between frames 0 and frame 1. Now, what about the transformation between frames 1 and frame 2? This is where we have frame 2, this is where we have frame 1. So what are the DS parameters corresponding to the transformation between frames 1 and 2? Okay, again, the first is the rotation about Z1. Rotation about Z1 to make uh, Z2 and Z1 align. And like since they are already parallel, since these revolute joints are already parallel, we don't need to rotate about X1 to make Z1 and Z2 parallel. So again, that is also 0. Alpha I minus 1 is 0. Then the next would be translation along X1 axis, right? Now that I is 2, translation along I minus 1, which makes it 2 minus 1 as 1 along X1 axis to make them coincide would be this link length L1. If I call this link length to be L1, you need to translate L1 along X1 so that frame 1 and frame 2 can come together. So AI minus 1 would be L1. Now what about theta 2? So once you have translated this frame 1 over to frame 2, it will be like this. Z1 will be along this axis. X1 would be along this axis. So X1 and X2 have an offset have a angular offset of theta 2, right? This is X2. X1 is like this after the after the translation. So you need an angular offset theta 2 so that X1 can be aligned to X2, and that accounts to theta 2. Now they are fully coincidental. You don't need any further transformation or any further translation along Z2. So that makes it 0. Right. And the final translation between Z2, this is Z2 out of plane. X2 will be along this link length. X3 will be also aligned. X3 will be aligned with X2. Z3 will be aligned to Z2. And now the final transformation to align frame 2 to frame 3 is simply a translation along X2. That's all we need. All the other things are already aligned by our choice. So final row would become 0. L2, theta 2, and 0, right? And once you multiply out, this will be 0 T1, second row would be 1 T2, third row would be 2 T3. And if you want to obtain the position and orientation of the frame 3 with respect to frame 0, you only need to multiply the individual transformation matrices 0 T1, 1 T2, and 2 T3. And once you do that, you will get the position coordinates as L1 cos theta 1 plus L2 cos theta 1 plus theta 2. This will be Px, and Py would be L1 sine theta 1 plus L2 sine theta 1 plus theta 2. This would be Py, and Pz would be 0 because this manipulator is actually a planar manipulator. It cannot come out of plane. Okay, so Nikhil has asked to upload the recordings of the meeting by today itself. Yeah, I'll do that. I'll upload the meetings by today itself. No problems at all. So yeah. And one thing is that, like, for a simple manipulator like this RR mechanism, you don't even have to derive the DH parameters or the DH metrics. You can simply write down what is Px, Py simply by looking at the geometry itself, right? Because this x-axis would be, this distance plus this distance. And this distance is nothing but L1 cos theta 1. And this distance, horizontal distance, would be L2 cos theta 1 plus theta 2. So this total x distance would be sum of L1 cos theta 1 plus L2 cos theta 2. And what about the y-axis? This vertical displacement would be sum of this distance and this distance, right? So this will be L1 sine theta 1, and this displacement, right? This would be L2 sine, that would be L2 sine theta 1 plus theta 2. So for manipulators like this, it is pretty straightforward. But if you have more number of links, maybe for example 4 or 5 or even 6 degrees of freedom, you cannot simply solve it purely by its geometric configuration, because it becomes far too complicated. So in order to do that, you will require a systematic construction of this DH table or this DH parameter table, and then substituting each of these parameters, right? You have to substitute each of these parameters into the matrix over here, right? Corresponding to which I you are dealing with. And once you do that, you multiply it successively. So you will get all these individual matrices. 0 T1 you will get 1 T2, you will get 2, 3, 3. And finally, you will have to multiply it one after the other. Yeah, that's about it. And okay. Okay, I've got one question from Venkata Lakshmi. Why theta is needed for frame 3? For theta, frame is not needed for theta 3, but yeah, theta is not needed. Exactly. I think I made a mistake over here. This is 0. Yeah, that is 0. Thanks for pointing out that, because frame 2 and frame 3 are already aligned. The only it's already aligned. The only thing is just this distance. That is only thing that is to be taken care of, and that can be taken care of by this parameter L2. Theta 2 need not be here. Theta 1 and theta are here in the preceding section. Yeah, and the only thing that is to be taken care of is this link length. I'll label this as L2. Okay, yeah, we have one more example over here, but I'm a bit worried about the time that we have. Yeah, we'll try to solve this. So this is basically an RRP manipulator. or you can also call this as a spherical manipulator, right? Because if you consider this entire part together, it can rotate about this vertical axis. So it can rotate, it can reach something like this, out of plane. And there is also prismatic joint like this. So it can slide like this, back and forth, right? This entire thing can slide back and forth. And one another thing that you should notice is that there is no uh, single way. You can assign this frame multiple ways. There is no unique way to assign frames and DH parameters in robotic manipulators. There could be multiple ways, multiple different ways as well. So I hope you can visualize this robotic manipulator. Maybe if I draw the links like this, we have a pedestal like this. I'll label this, and we have uh, a join like this. Okay, so we have one link that rotates. I'll also draw a fixed link like this. So this is the ground. This is basically part of the ground. So how many links do we have? We have the ground link. This entire thing is the ground link. You can consider this to be link 1, which will rotate about a vertical axis. I'll call this as maybe Z1, because link 1 can rotate about this vertical axis. And there is kind of a cylinder kind of a thing like this, right? Which will rotate like this, right, along this axis, right? So it can rotate, it can go like this, or it can go like this, up and down about this axis. I'll label that as Z2. And there is also one more link. I'll label this as link 2. I'll label this as link 3. And link 3 is connected to link 2 by a prismatic joint. It can slide back and forth like this, right? So like there are three number of links. Three links is actually possible. And in essence, as per the formula for an ND of manipulator, general thumb rule would be to have n plus 2 frames. But it's also possible to model it with fewer number of frames, as I can show that. Because it's not always it's not, in some cases you can have fewer number of frames than n plus 2. So how do we do this? We will start assigning the ground frame of reference, or for example, yeah, in this case we will stick with the convention. We will first identify the axes. So this is the first axis of rotation about the vertical axis. This is the second axis of rotation, and this is a third axis of translation, right? So we'll assign the first frame of reference. So yeah, I'll attach a frame Z0 like this. Sorry, Z1 for the first link. So I hope you can see this is the first link, and it is rotating about the vertical axis. So I'll attach a frame Z1 about the vertical axis. And this is the second link, which will rotate about this axis, Z2. So I'll basically have Z2 over here like this, like so. And Z3 would be along this axis because it's a translational join. So I'll attach Z3 over here, Z3. Now we also need to attach one more frame, that is ground. So like for convenience, I'll attach Z0 like this, Z0, which is the ground frame of reference. Okay, now how do we locate the x-axis? How do we locate the x-axis? Now to locate x1, we need to consider the perpendicular distances between x1 should be perpendicular to Z2 and Z1. So this is Z2, this is Z1. The perpendicular distance would be along this direction, right? So I'll use the red marker. I'll call this as x1. This is perpendicular to Z1 and Z2 and Z1. And what about x2? X2 can be perpendicular to Z3 and Z2. So I'll mark x2 like so. And Z3 and Z2, X3, I can mark it like this for convenience because they can be, they are aligned. Makes our job easy. Now, how do we assign the DS parameters? So the 4 DS parameters are alpha I minus 1. So I'll label it here, alpha I minus 1, AI minus 1, DI or theta I, DI. So I'll just write it somewhere better. Alpha I minus 1, AI minus 1. This would be theta I. This would be DI. And I would be here. And the first two would be transformations would be along xi minus 1. And the remaining two would be along zi axes. Okay, so yeah, we also need to fix x0. For convenience, I choose it to lie parallel to x1. So what would be the transformation between the 0th frame and the first frame? So the first row corresponds to the transformation. I labeled it here 0t1, right? And you can also consider this to be coincident. The 0th frame and the first frame, you can always consider it to be coincident because you can always fix the ground frame wherever you want. It does not make any difference. I'll also label this to be coincident. So, okay. And due to the fact that the frame, the first frame is mounted on the first link is actually free to rotate. And this Z1 can be like this. It can be anywhere within this plane. And it will be defined by this angle theta1. Right? It need not be always like this. It need not be always like this. The x1 will rotate about Z1 as the link one also rotates. So it can be like this, theta1, it can be like this, theta1, it can be anywhere along that horizontal plane. Then how do you map between the frame 0 and frame 1? So the first transformation would be the rotation about x0 so that Z0 and Z1 can be aligned. So since it is already aligned, Z0 and Z1 are already aligned, you probably don't need any rotation about x0. So alpha I minus 1 would be 0. and ai minus 1, which is the translation along x0. And since again they are coincident, you don't need any translation along x0. So ai minus 1 would also be 0. And theta I, what about theta I? Because as I've already said, x1 is free to rotate about z1 axis. So in order for x1 to match or to map x1 at any arbitrary orientation, you need to rotate x0. You need to rotate x0 by an angle theta 1 about z1. So that makes it theta 1. And di is also 0 because we have already established that the frame 1 and frame 2 are coincident, right? So that is 0t1. Now what about 1t2? The transformation between frame 1. So this is frame 1. Frame 1 would be, x1, z1 and x1. And frame 2 would be z2 and x2. Okay, now the first transformation would be again rotation about x1. So if you so that z1 and z2 can be aligned. So if you rotate 90 degrees by x1, so z1 will be rotated like this, and z1 and z2 would be aligned, right? So you have to rotate this by pi by 2 radians. So this is I as 1, this is I as 2. And now what would be the translation? Now, like for example, I'll label this as I'll label, once we have rotated, this will be z1 dash, right? Z1 dash and x1. Now ai minus 1 would be translation along x1, right? We don't need to translate along x1 because they are actually lying in a vertical line, and you don't need to translate any further along x1 because the distance between frame 2 and frame 1 are 0 along x1. So that makes this 0. And what about theta? Theta would be the angle between x1 and x2 along z2, right? And since this is also a revolute joint, this x2 can be anywhere within this vertical circle. It can be here, it can be here, it can be here, and that relative position is measured by this parameter theta 2. And there is already a 90-degree offset between x1 and x2, right? X1 and x2, there is already a 90-degree offset. So the total orientation between x1 and x2 along z2 would be pi by 2 plus theta 2, right? So once you rotate x1, it will be something like this. I'll label it like this, x1 dash. So now we have z1 dash and x1 dash. Now they are fully aligned, but we also need to, we also have this offset. And the only remaining transformation is along this D, Z2. So how do we do that? So with this sort of frame arrangement, that is not possible actually, because it's always going to be a trial and error process. So this offset, Z1 dash and X1 dash, it's aligned with Z2 and X2, but there is no way to compensate for this offset because our only remaining transformation is along Z2. This is our only remaining transformation. And our requirement is along this axis. So that makes it a bit of impossible. And we can actually do this by, bringing this x1 axis. We can shift this x1 axis to this point. It does not matter because we can always shift the frames along the joint axis. We can shift it up, we can shift it down. It does not make any difference. And the corresponding offset will be absorbed in the corresponding DS parameters. So just to give a quick overview of how this can be done, I'll just quickly redraw that. So the 0th frame of reference will remain as such as original. So this is Z0. This would be X0, just like earlier. Now I am bringing X1. I'm shifting X1 upward, like so. This will be Z1. X1 would be like this, right? Z2, sorry. Yeah, Z2 would be like this. And Z3, I'll attach Z3 over here. Again, for convenience, Z3. And X2 would be perpendicular to Z3 and Z2. So Z3 is along this direction. Z2 is along this direction. X2 would be hence parallel to Z1. This will be X2. And X3 I'll label this like this, just for convenience. And now how would our new DS parameters look like? This will be, alpha I minus 1, AI minus 1, theta I, DI, and for I as 1, I as 2. So the transformation between 0 and 1, how would it look like? So if I label this distance as L1, so what is the transformation between the 0th frame and the first frame? So the first would be rotation about X0 axis, so that Z0 and Z1 can be aligned. That is 0 because they are already aligned. Now, what about translation along X0? That is also 0 because they are again lying. There is 0 offset along X0, so that is also 0. And what about theta I? Because this is a translational joint, X1 can be anywhere, can be like this, defined by this angle theta 1. So the joint variable would be theta 1, right? And what about the distance along Z1? We have a finite distance L1 between these two frames, Z0 and Z1. And that can be accommodated using this parameter di. So I label this as L1. So yeah, I hope that is clear. And what about 1T2, the transformation 1T2 between frames 1 and 2? So the first would be rotation about X1 so that Z1 and Z2 can be aligned. So if you rotate 90 degrees by X1, this Z1 will be aligned to Z2. So that makes it pi by 2. And AI1 is basically the translation along X1. But we don't need that because both of them are basically coincident. Even though they are not fully aligned, they are coincident. So that is essentially 0. And what is theta I? Theta I is basically the rotation about Z2, so that X1 and X2 can be aligned. So this is X1, this is X2, and X2 can be at any arbitrary orientation parameterized by this angle theta 2, right? So, and there is already an offset 90 degrees between them. So 90 degrees plus this theta 2, that would be pi by 2 plus theta 2. And you don't need any further translation along Z2 because they are again coincident. So that also makes it 0. Now, what about 2T3? Transformation between frames 2 and frames 3. So the first would be to the rotation about x2 so that z2 and z3 can be aligned. So if I rotate 90 degrees about z2, sorry, x2, z2 and z3 will be aligned because they are 90 degrees apart. So that again makes it this for I is 3, this will be alpha minus 1 pi by 3. And AI would be the translation along x2. You don't need any translation along x2 because these two are aligned. There is 0 offset along x2. So that makes this 0. And what else do we have? Theta I, does x3 rotate with respect to x2? It won't rotate, right? Because this is a translational joint and x3 will always be parallel or will always be aligned with respect to x2. So theta I would also be 0 here again. And what would be the distance, offset distance between frames 2 and frame 3 along Z3? What would be that? This will be this distance actually.
D2, sir.
Yeah, D2. Exactly, D2. So the diagram is actually not clear. So the thing is, if you consider D2 to be this distance, if you consider D2 to be this distance, and if there is already one finite link length L2 here, you can consider it to be L2 plus D2. It's possible because when D2 is 0, the distance between the frames 2 and 3 would be just L2. Right? For example, if D2 is 0, distance between x2 and x3 would be simply L2. Or if L2 is non-zero, it will be simply L2 plus D2, however you want. It's not a big deal actually. Depends if you have a physical link length here or you consider your prismatic joint to be starting from this point itself. Whether you define D2 from here or whether you define D2 from here, that is all it matters. It does not. You can define it however you want. It's not a big deal. There are multiple ways to do that. Okay, so that is about it. And we'll solve some few, maybe 8 or 9 sample problems. These are very elementary simple problems. And you can expect, similar problems for the weekly quizzes. So the first question is, as per the DH representation, the kinematic arrangement of the manipulator contains only dash links. And each joint has dash degree of freedom. So if you wish to participate, you can participate. It's not a big deal. So if you know the kind of links that we are using for DH representation, okay, this may not be straightforward, but the answer is binary actually. Because links can be of different kinds. So binary links can only have 2 joints and it can only connect to 2 other links. There are ternary links actually with 3 joints, which can connect to 3 other links. There are quaternary links, which can connect to 4 other links. But in DH representation, we always assume that the links are always binary, like this. Right? So the manipulator is assumed to contain only binary links, and each joint has how many degrees of freedom? Again, like as per the assumption of this DH representation, each joint can only have 1 degree of freedom. And for complex joints like the ball and socket spherical joints, you can decompose it into 3 intersecting revolute joints. Okay, so checking the answers are here. binary is the answer. And over here, you can either type 1 or you can have that numerical 1 value, or you can even type it in as single. Either of these three choices, it will give you the correct answer. Or in case if you feel that you have written a different correct answer, but you have not been received any marks, you can always reach back to us. Okay, question 2. In revolute joint, what are the constant kinematic parameters? So is it the link twist? Is it the link length? Is it the joint distance? Is it the joint angle? Or are all of them constants? So like I'll simply represent a revolute joint like so. So this can be a revolute joint. This is another revolute joint. I label this as link 1. I label this as link 2. Link 1 as link length L1, as link length L2. This is Z1. This is Z2. And the relative orientation between link 2 and link 1, I label this as theta 2. Right? So yeah, I'll label this as Z1. This is Z2. This would be X1, which is along the common normal between Z2 and Z1. This is X2. So if you talk about this DH parameters, alpha I minus 1, AI minus 1, theta I, DI. And do you know which is which? Because alpha I, AI are simply that name of that variables. So link twist is this, alpha I minus 1, or the rotation about xi minus 1, that is link twist. And AI minus 1, or the translation along xi minus 1, it's called link length. That parameter is called link length. And theta I, or the rotation about Zi, is joint angle. And di is joint distance. So in case of a revolute joint, which of these parameters are varying? Is it possible to identify which of them is varying? Which of them is constant? Okay.
Theta will change, joint angle will change.
Yeah. Theta 2 will change. Joint angle will change. What about link twist? Because in case of a revolute joint, link twist does not really have to change. Because once you have a constant link twist, maybe 0, or it could be pi by 2, it'll always remain with that constant value. It does not really have to change. For example, if you have two joints like this, one along this, one along this, this is Zi minus 1, this is Zi. The perpendicular distance between these two would be 90 degrees. But once you have entered 90 degrees into the DH parameter, it does not have to change for any orientation. It'll always remain as 90 degrees. So like link twist is always going to be constant. And what about link length? Link length, obviously, it is also going to be constant. Because it's a rigid robotic manipulator, the link length is always going to be constant. Since it is rigid, it won't be changing. And theta 2 for a revolute joint is going to change because it's a revolute joint. It can rotate. It can rotate. At one configuration, it will be like this. At a different configuration, it will be like this. At a different configuration, it will be like this. So this theta 2, the value of that theta 2 is always varying. And the joint distance similarly is going to be a fixed constant for a revolute joint. It does not really have to change. right? So the only variable for a revolute joint is theta 2 or the joint angle. All the other things are constants. Whereas in the case of a prismatic joint, the joint distance or the translation along Zi is varying, right? Joint distance is the variable for prismatic joints, and joint angle is the variable for revolute joint. So the question asks the constant parameters, and in this case, the correct answer is link twist, link length, and joint distance. I think the option is link twist, link
C.
length,
C.
and yeah,
C.
option C, yes. Right? You can expect similar sort of questions for the weekly quiz. Okay, question 3. Dash is the perpendicular distance from xi minus 1 to x-axis measured along zi. So like similarly, you have link twist, you have link length, then you have joint angle, then you have joint distance. Right? And this is also as per the order of the transformation that you would be doing. Okay, one more thing. We may also have one more final interruption within 10 minutes. I'll try to wrap it within 10 minutes. If it is not the case, please join back. I'll try to wind up the session by 5 o'clock. Okay, based on the convention, the order of the transformation is first would be the link twist. The second would be to accommodate link length. The third would be to accommodate the joint angle. The fourth would be to accommodate the joint distance. And which of them is the correct answer for this specific question? Dash is the perpendicular distance from xi minus 1 to xi measured along zi axis. So the first two are always about xi minus 1 axis, and the second is always about zi axis. Right? The first attribute is rotation about xi minus 1 axis. This is translation about xi minus 1 axis. Joint angle is rotation about zi axis. This is translation along zi axis. And the question says it's the perpendicular distance from xi minus 1 to xi measured along zi. So it's something to do with distance, and it also has something to do with zi. So the correct answer, I believe, would be joint distance. Would you agree on that? Because to be
Sir,
more
can you
specific, sorry.
previous slide, sir? We can guess whether
Okay. The previous slide, this one.
okay, okay, sir.
Yeah. So, here in this example, the joint distance does not really apply because like there is no offset between frames 1 and frame 2 along Z2. They are always lying along this line. So like there is no offset. But if you can really recall what these definitions mean, link twist is rotation about xi minus 1 axis by an amount alpha I minus 1. Link length is translation along xi minus 1 by an amount ai minus 1. Joint angle is rotation about zi minus 1 axis by theta I. And joint distance is translation along zi by an amount di. And this transformation. The first transformation is to make zi minus 1 parallel to zi. And the second one is to make the distance between zi minus 1 to eliminate the, or not to eliminate, or just the perpendicular distance between zi minus 1 and zi axis. And the third is to make xi minus 1 parallel to xi. And the fourth is to make the perpendicular, fourth is to accommodate the perpendicular distance between xi minus 1 and xi. Right? So once you do all these four transformations successively, the I minus 1 frame and the ith frame will be perfectly aligned. And like this is actually as per the definition, as per the convention of the DH representation. And I hope you will agree that joint distance is actually the correct choice, is the most fitting for this fill in the blank, right? It is to accommodate the perpendicular distance between xi minus 1 and xi along zi axis. Okay, so yeah, checking the answer, it is indeed joint distance. You can expect similar questions for other definitions for the exam. So I would recommend you to be thorough with what each of these individual transformations are doing, which would be helpful. Question 4, a disadvantage of something is the transformation matrix is a mix of I minus 1 and ith indices. So this we have already discussed when we compared the standard and non-standard method. And you can actually say that this is a disadvantage of non-standard DH method, because that DH homogeneous transformation matrix will have indices I minus 1 and I. It's a mixture of that. So that is about it. Question 5. It's basically a vector algebra question. If two vectors are orthonormal, then what is the correct option? So I'll label this as V1. This is V2. And orthonormal in the sense they are normal to each other and their magnitude is 1. No, their respective length is 1. So which of these options are correct?
The dot product is 0.
Dot product is 0. What about their cross product? So V1 cross V2 sine 90. This will be V1 cross V2, right? And since they are orthonormal, their magnitude is actually 1. So it will be sine 90. That will be 1. So their cross product is also unity if they are orthonormal. So like you have two correct answers, right? So like be careful when you approach the weekly quizzes, because for questions having multiple correct choices, the radio buttons would be square like this. So like you can select multiple answers, but for a single correct answer questions, the radio buttons would be square kind of a type. You can only select one, one option. Yeah, so those are indeed the options. Correct answers, options D and D. Okay, now this is actually a numerical question. A triangle A and B with coordinates ABC is rotated about z-axis by 90 degrees, counterclockwise. Now the new coordinates can be described by which of these are the correct options? So for representation, I'll draw the triangle like this. So this is coordinate A0, 0, and this will be B. Sorry, B would be 3, 0, and C would be 3, 4. This is, I believe it's correct. C is 3, 4. Yes, this is the triangle. And if you label this as X, if you label this as Y, you are asked to rotate the triangle 90 degrees with respect to Z axis. So if this is X, this is Y, Z axis would be out of plane, right? So how would it look like it if you rotate it by 90 degrees? This would be something like this.
On the top, B will come, B will come.
Yeah, this will be B, right? What are the coordinates?
Now it is 0,3.
Yeah. This will be, yeah, 0, B would be 0,3.
Then C will be minus 3,4.
Minus 3,4, like this.
A is as usual.
So this is A, this is B, this is C. Like this.
Yes, sir.
Okay, are you sure that this is the correct answer, minus 3,4?
I will check. I will check. I
Yeah,
will check.
how do you check this actually?
Because you
can you
are
use rotation matrices?
Z axis means,
Yeah.
okay, I have not used the mathematical part, just my guessing only.
It's always advisable. Z axis would be something of this form: cos theta minus sin theta, sin theta cos theta. Is this fine? Would you agree with this? Or would you like to know more about how this matrix was obtained?
Morning, I watched the videos. I will try. Okay.
Okay, like the thing is to make this rotation matrix, like if you have two frames of reference like this, so this is X1, I'll use a different ink for more clarity. Yeah. So if I call this as X1 and if I call this as Y1, and if you rotate this about a vertical, a normal Z axis, the new frames would be tilted like this. This would be Y2 and this would be X2. I hope this is agreeable. And since we are rotating by theta degree, this is theta. And
With respect to which plane, sir?
with respect to Z axis, with respect to Z axis, we are rotating with respect to one axis.
Okay.
So if this is theta, this will be 90 minus theta, and this will be theta, this will be 90 minus theta. So the way we construct the rotation matrix is, the thing is we construct it by columns actually. This is first column, this is second column, and this is third column, right? So the way we would do this, first we would consider the newly rotated axis x2, right? And we would do the dot product of x2 with respect to x1, then y1, then z1.
Yes, sir.
Right. So what is the dot product of x2 with respect to x1? That would be x2 x1, then cos this one, right? Cos theta.
Yes, sir.
So since x2 and x1 are unit vectors, it will be simply cos theta.
Yes, sir. Yes, sir.
Then what would be the second element of the first column would be the dot product of x2 with respect to y1, right? That would be x2 x1 cos 90 minus theta, this one. What would that be? Projection of x2 on y1. Okay, I think I've made it a different made a mistake actually. I'll by sticking to that standard, I'll just simply keep this as x1. Y1 would be like this. Then x2 rotated would be like this. Y2 rotated would be like this. Right? So we are rotating it with respect to z-axis. Z-axis is out of plane. And this is theta. This is 90 minus theta. This is theta. This is 90 minus theta. So the first element here is the angle projection of x2 on x1. That is cos theta. And the second entry would be projection of x2 on y1. This component or this component, that is sine theta, right? Projection of x2 on y1 is sine theta.
Okay, sir. Sin theta.
Sine theta. And the third component here would be projection of x2 on z1. Z1 is out of plane.
Yes, sir.
So that is perpendicular. So it's 90 degrees. So it will be 0. Right? And coming to the second column, now we will take y2 with respect to x1, y1, and z1. So what is the component of y2, projection of y2 along x1? Y2 along x1 would be this component. Right? This component is cos 90 minus theta. That is sine theta, right? Since this is cos 90 minus theta, cos 90 minus theta is sine theta. And since this is actually facing opposite direction to x1, this will become minus sine theta.
Okay, sir.
Minus sine theta. And now projection of y2 on y1. This is theta. Projection of y2 on y1 would be cos theta. Cos theta. And projection of y2 on z1. Z1 is out of plane. That will be 0. Yes. That will be 0. And now the third one would be projection of z2 on z1. So sorry, z2 on x1. So since we are rotating with respect to z-axis, z2 and z1 will be always aligned.
Yes, sir. 0, 0, 1.
Yeah, 0, 0, 0, 1. So this is the rotation matrix about z-axis.
Yes, sir.
And similarly, you can find the rotation matrix about x-axis and y-axis. So,
Shall we put 90 now here, sir?
Yeah, here you can put 90 actually. So and one more thing, since the problem is 2D, we only need to take this much. We don't need to consider the full 3x3 matrix because our coordinates are 2D. So like we can extract this much out of the rotation matrix and then deal with these coordinates. These are 2D coordinates because it only has x and y components.
So rotation matrix into position matrix. We have to find, if we have to find the coordinates.
Yeah. So if you substitute 90 into this, what will you get? Cos 90 is 0. Sin 90 would be there is one here, then sin 90 is 1, then cos 90 is 0. Right? So there are 3 coordinates. The first is 0, 0.
Yes, sir.
So 0, 0, if you do that.
Okay, there is no change. Okay,
That
0,
is
0.
0, 0 itself. So 0, 0 is answer. If you put, what will you do?
3, 3, 3, 0.
3, comma 0.
Until now.
What will you get?
0, 3.
0,
We are getting 0.
Yeah.
So
Then
that is okay, sir. Then
now if you
3,
put 3, 4, What
Then
will you
3,
get?
4.
You will get
-4,
minus 4,
minus
3.
4 and 3. But
Yeah.
here we got in the graph -3, 4, sir.
But
So
is it
that is
correct
wrong.
though?
So whatever triangle we have represented is wrong. We have to show
Uh,
the bottom part, sir. Bottom part.
Whatever triangle we have shown is probably wrong. Yeah, I think so. Yes.
The shading.
Shading should come at the bottom.
Actually, 03 is in 03 is what is wrong here. 0003.
I think it's correct. The representation is correct, I think. If you rotate it like that,
03. Then -4, 3. 01. -4, 3. So what is -4? X-axis is -4. And then it is 3.
right?
I will try, sir. I will try to go.
Okay. If there is any mistake, please let me know. You can reach back to me through the discussion forum. We can
Okay, sir.
rectify that.
Sir, I
Okay. So the
have
answer is sorry.
a single doubt, sir. So we are electronics students with
Yeah.
interest. I opted this one. I have a fear whether I can complete this course
Oh,
or not.
it's actually an easy course. It's not a big deal. Like once you practice this enough, then all these problems are not that difficult actually.
Okay, sir.
Right? If you refer to any standard textbook, there will be numerous problems. Or if you simply solve some problems that is being discussed in the in the live lectures
Okay, sir.
by the professor, I think it should be pretty
Yes, sir.
easily solvable. It's not a big deal.
With your live interaction and with his teaching, so we are getting the double the time, the experience, sir.
Okay,
So
okay. So if you have
from
any
the live
further
interaction.
questions, yeah, you
Okay,
can
sir.
raise it on the discussion forum.
Okay, sir.
The TAs, including myself, we can answer that in case if
Thank
you
you.
have any doubts.
Okay, sir.
So that is the answer. Moving on to question 7. The question 7 says, find the twist angle for the given frame arrangement as shown in the figure. So the twist angle is basically, what is the twist angle? Twist angle is the rotation about xi, rotation about xi by xi minus 1 by alpha I minus 1, so that zi minus 1 and zi can be aligned. That is the twist angle, right? If you recall the DH representation, the successive transformation are the first twist, then the link length, then the joint angle, then the joint distance. So here, Z1 is like this, X1 is like this, Z2 is like this. So twist is basically you want to rotate about X1, right? So that Z1 and Z2 can be aligned. That is the twist. So out of these options, which is the correct option? Remember, the twist angle only deals with the alignment. It does not deal with the displacement or the distance. So which of them is the correct answer? Any options?
Maybe the pi by 4 or
Pi by 4
alternate.
means if you rotate by x1 about pi by 4, it will only be 45 degrees, right?
Okay, sir.
Positive axis would be, if you do this right hand rule,
Negative.
right
Okay,
hand
sir.
screw rule, this is positive rotation. And positive rotation means x1 would be 45 degrees from here, right? And if you rotate by 90 degrees, x1 would be like this. This would be x1. And if you rotate 180 degrees, x1 would become vertically straight below. This would be x1, right? And if you rotate 270 degrees, x1 would come like this. Sorry, z1 would come like this. So which of these options are correct? So this is 90 degrees, this is 180 degrees, this is 270 degrees. So the answer is, Kiran has said the answer to be 270 degrees, and 270 degrees accounts to 3 pi by 2, right? In radians.
That is
I
the
hope that is
problem,
clear.
sir. Visualization, electronic students visualization, it looks
Yeah,
only in the 2 dimensions.
yeah, everything looks in 2 dimensions. But if we draw a vector like this basically means it's going out of plane,
Okay, sir.
right?
Okay, sir.
2D will be parallel to the drawing board. This 2D will be always parallel to this axis and this axis,
Okay.
and anything going in this direction should be out of plane,
Okay. Thank you, sir.
right? Yeah. So 3 pi by 2 would be the answer because you have to rotate it by 370 degrees so that Z1 will be parallel to Z2. Moving on to question 8, find the link twist angle and the link length for the given frame arrangement as shown in the figure. So link twist, again, similar to what we have said. Link twist is rotation about x1 by an angle alpha 1 so that Z1 and Z2 can be aligned. And link length would be the translation along x1 by maybe a1 so that the perpendicular distance between z1 and z2 can be accommodated, right? And the successive transformation, as I've said earlier, it is first we do the twist, then we will do the link length, then we would do the joint distance, joint angle, then we would do the joint distance. So first, as per the succession, we have to first do the link twist. So the link twist, we have to rotate about x1 so that z1 and z2 can be aligned, right? So since this is the direction of x1 is along this direction, the positive rotation would be like this. Positive rotation as per the right hand screw rule would be like this, right? So by how many degrees do you have to rotate Z1 so that Z1 and Z2 would be parallel? About X1. And note that X1 is actually out of plane. X1 is perpendicular to the plane. So if you want to rotate X1 perpendicular to a line, that is perpendicular to the plane, and if you want to rotate it like that, what would be the link twist angle? So if this is x1, if you rotate by 90 degrees, z1 would be like this. If you rotate by 180 degrees, z1 would be like this. If you rotate 260 degrees, z1 would be like this, right? And full 360 degrees would be like this. Kiran has said it to be 0 and L. So if you rotate z1 by 0, Z1 is like this, Z2 is like this. That alignment is still not taken into effect, right? You have to rotate by x1 so that Z1 and Z2 will be aligned. 0 means they still have that 90-degree offset, right? Z1 is like this, Z2 is like this. So you have to rotate by 90 degrees, right? You have to rotate Z1 by 90 degrees so that Z1 and Z2 can be aligned. Right? I hope that is clear about X1.
Okay, sir. 90 degrees.
Okay. So twist would be 90 degrees. Then what is the second one? Link length. Link length is also about X1. Link length is also about X1 so that the perpendicular distance between Z1 and Z2 can be accommodated. So just for the sake of understanding, now that we have rotated 90 degrees, the new X1 would be like this. New Z1 would be like this. You can simply, uh, ignore this Z1 because we have already rotated about like this, right? And now link length would be the distance along X1, distance along X1, so that the perpendicular distance between Z1 and Z2 can be accommodated. So now this is Z1, this is Z2, and this is actually out of plane. The perpendicular distance is that. This is
That is
90
K.
degrees. That will be K. Yes, correct. So link length is K. This is pi by 2. So the answer is pi by 2 and K for twist angle and link length. So I hope that is clear. If you check the answer, option A is indeed correct. And moving on to the final question for this session, dash is the angle between xi minus 1 and xi measured about zi. So just to bring everything into context, the successive order of transformation are the rotation about xi minus 1 by an amount alpha I minus 1. Then we have translation along xi minus 1 by ai minus 1. And we have rotation about zi by an amount theta I and translation along zi by an amount ti. And we call this as twist or link twist. This is link length. This is joint angle. And this is joint distance. Right? And the first two rotations, if you can see the suffixes, the first two transformations are about xi minus 1, and the second two transformations are about zi. So our answer essentially lies in either in this third or the fourth answer, because it's something that is measured about zi, right? And it also says it's an angle between xi minus 1 and xi, right? Angle
Then
between xi minus 1 and xi.
joint
So
angle.
joint angle. So this is nothing but the definition of joint angle. So there is no other way to correctly learn about this apart from learning the definition and to apply how these definitions into DH parameters. But to solve the question, this is actually a short trick because you can actually it's as per the definition. The first two translations are about xi minus 1, and the second two transformations are about zi, right? And the question asks about something that is measured about Israel, and it also says it's an angle. So the only option that possibly fits all of these constraints are joint angle. Yeah, so that is indeed the answer of that. Yeah, so we have come across all the 9 questions for this session. Yeah, I think I also may have overstayed uh, the duration of this session, so I apologize for that. So yeah, with that, I would like to wind up this session. If you have anything else to add, please let me know. Uh, Otherwise, yeah, thank you for joining. So yeah, if there is anything else, shall I wrap? Okay, thank you. Okay, thank you very much. So with this, I'll wrap up the session. Thank you for joining. We'll see next week. Okay, thank you.